Sklearn calibration. Description. Explain in detail. Calibration refers to the process of adjusting the outputs of a machine learning model to better align with the true probabilities of the events being predicted. This is particularly crucial when dealing with probabilistic models, such as logistic regression or support vector machines, where the model's outputs represent the probability of a particular class or outcome. Calibration ensures that the model's predicted probabilities accurately reflect the likelihood of the event occurring in the real world. Inputs. Input 1. Explain in detail. The input to calibration is a trained machine learning model, typically a probabilistic model like logistic regression, support vector machines, or a decision tree. This model should have been trained on a labeled dataset and is ready to make predictions on unseen data. Input 2. Explain in detail. Additionally, a set of labeled data is required for calibration. This data should be independent of the training data used to train the original model. It serves as a reference point to adjust the model's predictions based on its performance on this new dataset. Outputs. Output 1. Explain in detail. The calibrated model itself is the primary output. This is the adjusted version of the original model, where its predictions are recalibrated to align better with the true probabilities of the events. Output 2. Explain in detail. The calibration process often provides various metrics that measure the quality of calibration. These metrics quantify how well the model's adjusted predictions match the observed probabilities in the calibration dataset. Common metrics include Brier score, calibration plots, and reliability diagrams. Steps. Step 1. Explain in detail. The first step involves obtaining predictions from the original model on the calibration dataset. The model generates predicted probabilities for each data point in the dataset. Step 2. Explain in detail. The calibration step adjusts these predictions based on the observed outcomes in the calibration dataset. This adjustment can be achieved using various techniques, including Platt scaling. Fits a sigmoid function to the original model's predictions, mapping them to calibrated probabilities. Isotonic regression uses a monotonic function to adjust the predictions, ensuring that the calibrated probabilities are non-decreasing as the original model's predictions increase. Histogram binning divides the predictions into bins and adjusts the probabilities within each bin based on the observed outcomes in that bin. Metrics. Metric 1. Explain in detail. Brier score. This metric quantifies the mean squared difference between the predicted probabilities and the actual outcomes. Lower Brier scores indicate better calibration. Metric 2. Explain in detail. Calibration plots. Visualize the calibration by plotting the predicted probabilities against the observed probabilities. Ideally, the points should lie close to the diagonal line, indicating good calibration. Visualization plots. Visualization plot 1. Explain in detail. Calibration plots. These plots are essential for visually assessing calibration. They depict the relationship between the predicted probabilities and the observed frequencies of the events. A well-calibrated model would have points close to the diagonal line, indicating that the model's predictions align with the true probabilities. Visualization plot 2. Explain in detail. Reliability diagrams. Similar to calibration plots, these diagrams illustrate the calibration performance. They show the average predicted probability for each bin against the observed frequency of events in that bin. A well-calibrated model would have points close to the diagonal line, suggesting that the model's predictions are reliable across different probability ranges. Fine-tune parameters. Parameter 1. Explain in detail. Number of bins when using histogram binning. The number of bins significantly influences the calibration. Too few bins might not capture subtle variations in the model's predictions, while too many bins might lead to overfitting the calibration data. Experimenting with different numbers of bins is essential to achieve optimal calibration. Parameter 2. Explain in detail regularization parameter in methods like isotonic regression. A regularization parameter controls the smoothness of the calibration function. Higher regularization values make the calibration function smoother, preventing overfitting to the calibration data but potentially sacrificing the accuracy of calibration. Uncertainty methods. Uncertainty method 1. Explain in detail confidence intervals after calibration. It is possible to estimate the uncertainty in the calibrated probabilities by constructing confidence intervals. This provides a range within which the true probability is likely to lie, giving a more complete picture of the model's prediction. Uncertainty method 2. Explain in detail Bayesian calibration incorporating prior knowledge about a model's parameters through Bayesian methods can provide uncertainty estimates. This approach allows for capturing the uncertainty in the model's predictions and the calibration process itself. Challenges and fixes. Challenge 1. Explain in detail limited calibration data. Insufficient calibration data can lead to inaccurate calibration, especially when the data is not representative of the true distribution of the events. Sample use case that resulted in Challenge 1. Imagine a model predicting the probability of a customer purchasing a product. If the calibration data consist mainly of customers who have already purchased the product, the calibration might be biased towards overestimating the purchase probability. Fixes to Challenge 1. Collect more calibration data. Gather a larger and more diverse dataset that reflects the real-world distribution of events. Use synthetic data. Generate synthetic data based on the existing data to augment the calibration dataset. Employ transfer learning. Leverage a pre-trained model that has been calibrated on a larger dataset to improve calibration with limited data. Challenge 2. Explain in detail overfitting to the calibration data. The calibration process might overfit to the specific calibration dataset, leading to poor performance on unseen data. Sample use case that resulted in Challenge 2. A model calibrated on a dataset with a specific distribution of events might perform poorly on a dataset with a different distribution. Fixes to Challenge 2. Regularization. Introduce regularization techniques to the calibration methods to prevent overfitting. This can involve using penalty terms that discourage complex calibration functions. Cross-validation. Perform cross-validation on the calibration dataset to evaluate the performance of the calibrated model on different subsets of the data. Use a simpler calibration method if overfitting is a concern. Consider using a simpler calibration method like Platt scaling instead of more complex methods like isotonic regression. Challenge 3. Explain in detail choosing the right calibration method. The choice of calibration method can significantly impact the calibration results. Some methods might be better suited for certain types of models or datasets. Sample use case that resulted in Challenge 3. Platt scaling might not be appropriate for models with high dimensional output spaces, while isotonic regression might be more suitable. Fixes to Challenge 3. Experiment with different methods. Try different calibration methods and evaluate their performance using appropriate metrics. Consult literature. Refer to research papers and documentation to understand the strengths and weaknesses of different calibration methods and their applicability to specific scenarios. Consider domain expertise. Incorporate domain expertise to guide the selection of the most appropriate calibration method for the task. sklearn calibration calibrated classifier CV. Description calibrated classifier CV is a scikit-learn estimator that uses calibration to improve reliability of probability estimates produced by a given base classifier. It does this by fitting a sigmoid function to the base classifier's predicted probabilities, effectively scaling them to better match the true probabilities of the target class. Inputs: base estimator, the base classifier to be calibrated. It can be any scikit-learn classifier that provides probability estimates. Method: the calibration method to use. It can be sigmoid or isotonic. Sigmoid fits a sigmoid function to the predicted probabilities, while isotonic uses a monotonic function that preserves the order of the predicted probabilities. CV: the cross-validation strategy to use. It can be an integer, a cross-validation object, or an iterable. Outputs: calibrated classifier, a calibrated classifier object that combines the base classifier with a fitted calibration model. Calibrated probabilities: the calibrated probability estimates output by the calibrated classifier. Steps: train the base classifier on the training data. Split the training data into folds using the specified cross-validation strategy. For each fold, use the trained base classifier to predict probabilities on the held-out data. Fit the chosen calibration model sigmoid or isotonic on the predicted probabilities and the true labels of the held-out data. Apply the fitted calibration model to the predicted probabilities of the entire training data to obtain calibrated probabilities. Metrics: Brier score measures the average squared difference between the predicted probabilities and the true labels. A lower Brier score indicates better calibration. Calibration plots visualize the relationship between predicted probabilities and observed frequencies of the positive class, helping to assess the calibration of the model. Visualization plots: calibration plots display the relationship between predicted probabilities and observed frequencies for each class, revealing the calibration performance. Receiver operating characteristic ROC curves show the trade-off between true positive rate and false positive rate for different probability thresholds. Fine-tune parameters. Method: choosing sigmoid or isotonic based on the data characteristics and desired calibration. Behavior: CV: adjusting the cross-validation strategy to optimize the calibration process. Uncertainty methods. Confidence intervals for calibrated probabilities, quantifying the uncertainty associated with the calibrated probability estimates. Bootstrap aggregating, bagging, or other ensemble methods combining multiple calibrated classifiers to reduce the variance of the predictions and improve uncertainty estimates. Challenges and fixes. Challenge 1: insufficient data for calibration. Sample use case that resulted in challenge 1: when the dataset is small or imbalanced. There may be insufficient data to accurately fit the calibration model. Fixes to challenge 1: use a larger dataset for training if possible. Consider using a more robust calibration method that is less sensitive to data scarcity. Use data augmentation techniques to artificially expand the training data. Challenge 2: overfitting the calibration model. Sample use case that resulted in challenge 2: when the calibration model is too complex or the data is noisy. It may overfit the training data and lead to poor generalization performance. Fixes to challenge 2: use regularization techniques to prevent overfitting. Consider using a simpler calibration model. Use cross-validation to select the best hyperparameters for the calibration model. sklearn. Calibration. Calibration curve. Description. The calibration curve function in scikit-learn sklearn. Calibration. Calibration curve is a powerful Tool for evaluating the reliability of probabilistic predictions from classification models. It essentially plots the true positive rate TPR against the predicted probability of being positive. This helps to assess how well the model's predicted probabilities align with the actual observed probabilities. Inputs. Why true? This is a 1D array containing the true labels of your data. The values in this array should correspond to the target variable you are trying to predict. For example, if you are classifying spam emails, this could contain values like spam or not spam. YP-red proba. This is a 2D array or a list of 1D arrays representing the predicted probabilities for each class. In the case of binary classification, each row would have two columns: the predicted probability of being in class 0 and the predicted probability of being in class 1. NB-ins. This parameter determines the number of bins to use for creating the calibration curve. More bins generally offer a more fine-grained analysis, but too many bins might lead to noisy results. Strategy. This optional argument allows you to specify the binning strategy. The default strategy uniform creates bins of equal width. Alternatively, you can choose quantile to create bins with an equal number of samples in each. Outputs. Prob_true. This is a 1D array containing the average true probabilities for each bin. These represent the actual observed probabilities of positive samples within each bin. Prob_perd. This is a 1D array containing the average predicted probabilities for each bin. This represents the average probability assigned by the model to samples falling within that bin. Bin edges. This is a 1D array containing the bin edges, which define the boundaries between the bins used to create the calibration curve. Steps. Binning. The calibration curve function first divides the predicted probabilities into bins based on the chosen strategy, e.g., equal width or equal frequency. Averaging it then calculates the average true probability prob_true in the average predicted probability prob_perd for each bin. This averaging process is done separately for the positive and negative classes. Visualization. The function does not directly create the visualization. Instead, it provides you with the data prob_true, prob_perd, bin edges that you can then use to create a calibration plot. Metrics. Calibration error. This metric quantifies the difference between the predicted probabilities and the true probabilities. It's often expressed as a measure of the distance between the ideal diagonal line and pay. Calibration curve. A calibration error close to 0 indicates a well-calibrated model. Visualization plots. Calibration plot. This is a standard plot created by plotting prob_true against prob_perd. An ideal calibrated model would exhibit a straight line along the diagonal. Deviations from the diagonal indicate biases in the model's probability estimates. Fine-tune parameters. NB-ins. Experiment with different values of NB-ins to find the optimal balance between fine-grained analysis and potential noise. Strategy. Choosing the appropriate binning strategy, uniform or quantile, depends on your dataset and the specific characteristics of your model. Uncertainty methods. Confidence intervals. You can add confidence intervals to the calibration curve to assess the uncertainty associated with the estimated probabilities. Libraries like Sci-kit learn can assist in calculating these intervals. Challenges and fixes. Challenge 1. Challenge description. Inadequate binning can lead to a distorted calibration curve, making it difficult to accurately assess calibration. Sample use case. A model with a very skewed distribution of probabilities might require a non-uniform binning strategy to capture the variations effectively. Fixes. Adjust the NB-ins parameter to find a suitable balance. Experiment with the quantile strategy for binning, especially when dealing with skewed distributions. Challenge 2. Challenge description. The calibration curve might be overly sensitive to outliers in the data, leading to misleading interpretations. Sample use case. A few extreme cases with very high or very low predicted probabilities could disproportionately affect the overall calibration. Fixes. Consider applying outlier detection techniques to identify and potentially remove extreme data points. Explore robust binning methods that are less susceptible to outliers. Use a larger sample size to mitigate the impact of outliers on the calibration. Challenge 3. Challenge description. Overfitting can lead to a calibration curve that appears well calibrated on the training data but performs poorly on unseen data. Sample use case. A model trained on a small dataset might overfit the specific data points, resulting in unrealistic calibration estimates on new data. Fixes. Use cross-validation techniques to assess the model's calibration on unseen data. Implement regularization methods during training to prevent overfitting. Increase the size of your training data to reduce overfitting. Challenge 4. Challenge description. The calibration curve might not be informative for highly imbalanced data sets, where the minority class is poorly represented. Sample use case. In fraud detection, where fraudulent transactions are rare, the calibration curve might not provide meaningful insights due to the limited number of positive samples. Fixes. Use specialized calibration techniques designed for imbalanced datasets, such as the Platt scaling method. Consider using resampling methods to balance the dataset before training the model. Focus on evaluating the model's performance on the minority class to gain a better understanding of its calibration in that context.